Hello and welcome to the second and final video of the M3 chapter Statics of Rigid Bodies. M2 exam question on the screen to get us going. A ladder AB of weight W and length 4A has one end on rough horizontal ground. The coefficient of friction between the ladder and the ground is mu. The other end B rests against a smooth vertical wall. That tells me straight away that friction down here is acting this way, because it would slide down if it could, and therefore this would slide out if it could, and friction always opposes motion. The ladder makes an angle theta with the horizontal, where tan theta equals 2. If I quickly sort out my angles over here, if this is a theta, to get tan theta equals 2, we need a 2 here and a 1 here, which would give us a square root of 5 over here. So the sine of theta is equal to 2 root 5 over 5, and the cosine of theta is equal to root 5 over 5, in case we need those later. A load of weight 4W is placed at the point C on the ladder, where AC is 3A. So here we've got 4W, where W is still the weight of the ladder itself. The ladder is modelled as a uniform rod, which means its weight can be in the middle. W, where this distance here to here is 2A. It's in the vertical plane perpendicular to the wall. The load is modelled as a particle. Given that the system is in limiting equilibrium, so the friction is at its maximum, mu r, show that mu is equal to 0.35. First thing I need to do is finish my diagram. There are two more forces to go on. That's the reaction here and the reaction here. Now I'm going to resolve. Resolving to the right gives us a very simple equation. Friction must equal the reaction S. Resolving upwards gives us R is equal to 4W plus W. We also have our friction equation, mu times R, which we now know is 5W. And to solve this, we still need more information, so we're going to have to take moments. It would be great if we could find out friction, so we can use this equation to find mu in terms of W. And friction is equal to S. So if I know S, I know friction. So to take moments, I'm going to take moments about point A, which will make it quite easy to find S, which in turn will give me friction. So moments about point A, anticlockwise must equal clockwise because it is in equilibrium. The anticlockwise moment is S, and that is at a distance, perpendicular distance, here, which is 4A sine theta. The clockwise moments, W and 4W, but they have different distances. So we've got W times 2A cos theta to get this distance here, plus 4W times 3A cos theta. All of the A's cancel out, and the terms on the right can add together, so we get 4S sine of theta is equal to 14W cosine theta. Now we know what sine theta is, and we know what cosine theta is, so I'll put them in now. That gives us 8 root 5S over 5 is equal to 14 root 5 over 5 W. Root 5s over 5 cancel, giving S is equal to 14 over 8, or 7 over 4 W. Now we know that S is equal to the friction because of a previous equation up here, and we're going to put that into this equation here. So 7 over 4W is equal to 5 mu W. The W's cancel. Divide through by 5 gives us 7 over 20 for mu. Converting into a decimal is 0.35 as required. In this video, we're going to determine whether a rigid body will slide or topple. And we're going to be considering the same 4 things as we had before, most of which we used in the starter question there, to solve these problems. Moments about one or more points, resolving forces in one or more directions, a friction equation or inequality, and the location of the center of mass of the object. Remember that an object on the point of toppling has its center of mass vertically above a single point of contact at the very edge of the base. So if you remember the work we've done in M2, if we've got an angle here that we're going to increase, we're going to bring this up like this, then the center of mass of this lamina, or solid object as it will be in this chapter, if the center of mass of the object is vertically above a point of contact with the base and the surface, then it will remain in equilibrium, assuming it doesn't slide. But once that center of mass is vertically above the final point of contact with the base, it's just on the point of toppling. And as soon as that center of mass is vertically above a point that is not in contact with the surface, it will topple. Remember also that an object on the point of sliding, which is also called limiting equilibrium, gives friction is equal to, not less than, mu times r. Friction is at its maximum when it's on the point of sliding. If it's not on the point of sliding, this has to be an inequality sign. A quick hint on two very particular scenarios. The first is if you are required to determine if and how an object with given conditions breaks equilibrium. First, consider the conditions for equilibrium, find all of the equations for equilibrium like we did in the starter question, and then look for contradictions. For example, if you find that mu must be a certain value in order for it to stay in equilibrium, and your given conditions tell you that mu is less than that value, then you know the object must slide. So consider it to be in equilibrium, find all of the appropriate equations, solve for equilibrium, then compare it with the conditions you've been given, and then see which one is not correct. Or if they are all correct, if they can all be correct at the same time, then it must remain in equilibrium. Second scenario, if you're required to determine if an object on an inclined plane with increasing angle topples first or slides first, then consider the two separate scenarios. Assume that the object will not slide and find the angle that it will topple. Then assume that the object does not topple and find what angle it will slide, and then just see which one happens first, i.e. at the smaller angle. These aren't the only scenarios you'll have, but if either of those do come up, there are some hints as to how to go about solving them. Our first example, a solid uniform cylinder of radius 3 cm and height 5 cm has a solid uniform hemisphere made from the same material, so they've got the same density, of radius 3 cm, joined to it so that the base of the hemisphere coincides with one circular end of the cylinder. So we've got quite a wide cylinder compared to its height, and the hemisphere stuck on one end. The radius of the two is 3 cm, and the height of the cylinder is 5 cm. Find the position of the center of mass of the composite body. So we're going to do what we did in the previous video. We've got the center of mass of the cylinder at its geometric center point, and the center of mass of the hemisphere 3/8 of the way up from the circular side. So that's 3/8 of 3, which is 9/8. I think in this case I'm going to use this as my origin, x-axis, y-axis. That's so that I can use this value for the center of mass of the hemisphere, but I must remember then that this is going to be a negative, and that will be negative 2.5 on the y-axis. Then we go back to the table. Cylinder, hemisphere, composite body. We're going to have the relative mass, so I won't bother putting in the rho. We're just going to use the volume because they are made of the same material. The volume of the cylinder is pi r squared times the height. Volume of the hemisphere, 2/3 pi r cubed. And adding those two together gives me 63 pi. The center of mass on the y coordinate, y bar here, minus 2.5 here, and 9 over 8 here. When we form our equation then, we get minus 225 pi over 2 plus 81 pi over 4 is equal to 63 pi y bar, which gives the final answer for y bar as minus 41 over 28, relative to this point here. Part B. The composite body is placed with the circular face of the cylinder on a rough inclined plane, which is inclined at an angle alpha to the horizontal. Given that the plane is sufficiently rough to prevent sliding, so we're being told outright that the object does not slide. Show that the equilibrium is maintained provided that tan alpha is less than 28 over 33. So if it definitely does not slide, then as alpha increases, to maintain equilibrium means we must ensure it does not topple. So we're going to try and find the angle at which the object would topple, and then we'll say, okay, it has to be less than that angle in order for equilibrium to be maintained. Going back for a second, we're going to need this distance then. If we had this distance relative from this point as minus 41 over 28, so the distance 41 over 28, take that away from 5 to get this distance here, and that gives us 99 over 28. That's probably going to be a more helpful value in this next part. So we've got the object here, alpha here, centre of mass here, and if it's just on the point of toppling, this centre of mass must be vertically above this final point of the base, right on the corner here. So that comes down just above there. And we know the centre of mass distance from this point here, and we know the radius of the cylinder. So if I pull that triangle out and blow it up a bit, centre of mass here, the distance down to the centre point 99 over 28 from part A. The radius we know is still 3, and what we want to find is this angle alpha here, which is the same as this angle here. Actually, we don't really want to find the angle alpha itself, we want to find tan of alpha. The tan of alpha is the opposite 3 divided by the adjacent, so tan of alpha is equal to 3 over 99 over 28, which is 28 over 33. So this is where the object is on the point of toppling. Anything bigger than this and it will topple. Anything less than this and it will not topple, which means equilibrium will be maintained. So our answer, tan of alpha, must be less than or equal to 28 over 33. And I think that must be a slight typo in the question, because I think this should be less than or equal to. If it's equal to, it's on the point of toppling, but it still has not yet toppled. Second example. A uniform solid cube of mass m and side 2a rests on a horizontal plane. So we've got our horizontal plane, and on here a cube of size 2a, mass m, the weight acting at its geometric centre because it's uniform. The coefficient of friction is mu. A horizontal force of magnitude P is applied to the midpoint of an upper edge perpendicular to that edge. So I'll put that here, and then we can consider this to be a view of the plane of symmetry in the middle, and I'll have these two acting in the same vertical plane. The reaction between the plane and the cube comprises a normal reaction force R and a friction force F, and acts at a distance h from the lower edge of the cube. Okay, let's have a look at this a little bit more closely. The reaction, singular, between the plane and the cube comprises, that means it's made up of, a normal reaction force, R, and a friction force, F, and acts at a distance, that's the reaction, so both of these act at a distance h from the lower edge of the cube. I'll make the lower edge the one down here, in the same vertical plane as these, so it's going to act at the midpoint, a distance h from there. These two forces are going to act. Let's have R here, F here, and that is a distance of h from this lower edge here. Given that p is equal to 1/3 mg and mu is equal to 1/4, determine whether the cube topples or slides or remains in equilibrium. What we're going to do here is assume that it does remain in equilibrium, solve for the things that we don't yet know, r, f and h, and then as we go see if there's any contradictions to what we've assumed. For example, if we find that h is less than 0 or bigger than 2a, then we know that can't be possible. Or if we find that the friction force is equal to something bigger than 1/4 times the reaction, then we know that can't happen either. If we don't find anything like that, then our assumption that it remains in equilibrium is okay. So let's see what happens. I'm going to start by taking moments about this point here, call that capital A, moments about A, anti-clockwise must equal clockwise. Anti-clockwise we've got the mass times g acting at a distance of A, perpendicular distance, and that's it, because F is going to act through this point, so that won't be involved in the equation, and R and P are both acting in the clockwise direction. So MGA must equal P times 2A plus R times H. And given that P is equal to 1/3 of mg, this becomes 2/3 mga plus RH is equal to mga, which gives us RH equal to 1/3 mga. Now we can resolve. Resolving vertically gives us upwards R minus downwards mg must equal 0, so R is equal to mg. Resolving to the right, P minus F must equal 0, so P is equal to F. And we know P, therefore we know F is 1/3 of mg. And we can also put mg for R in this equation to give mgh is equal to 1/3 mga, which tells us that h is equal to 1/3 of A. Here we've got two important pieces of information. We've got the distance h is equal to 1/3 A, and we've got friction is equal to 1/3 mg. Firstly, this is okay. 1/3 of A is a reasonable distance. If A is here, 1/3 of A is about here. And that's fine. There's no problem with that. That can happen. However, with this one here, remembering that R is equal to mg, we can make this equal to 1/3 of R, and that's the friction. That is a problem, because we've got mu is equal to 1/4, which means that the maximum friction available is equal to mu times R is equal to 1/4 of R. How then can we have friction as 1/3 of R, which is a bigger value than 1/4 of R? That cannot happen. The friction cannot get that high, which tells us that the cube must slide. That's how it breaks equilibrium in this example. And that is because the friction is greater than mu times R, which cannot happen. The next example uses a very similar cube. We've got a uniform solid cube, mass m, side 2a, placed on a rough inclined plane this time, which is at an angle alpha to the horizontal, where tan alpha equals 1/2. So here we've got our same cube, but now on an inclined plane. It's still 2a, the centre of mass is still at the geometric centre, the weight mg. Here alpha, where tan of alpha is equal to 1/2, and it is rough, so there is friction, and that will act up the plane if the box is trying to slide down the plane. The coefficient of friction is mu, so our maximum friction is mu times R, where R will be going this direction. Show that if mu is less than 1/2, the cube will slide down the slope. We just need to split our weight into two components. We've got this way perpendicular to the plane, mg cos alpha, and this way acting down the plane, mg sine alpha. Then if we resolve parallel to the plane, we get mg sine alpha minus friction equals 0 in equilibrium, so that must equal friction. Resolving perpendicular to the plane, we have mg cos alpha minus r must equal 0, so that must equal r. Then putting them together into the friction equation, for limiting equilibrium, friction is equal to mu times r, mg sine alpha is equal to mu times mg cosine alpha. Divide through by the cosine, we get tan alpha is equal to mu, and we know tan alpha is equal to a half, therefore mu is equal to a half in limiting equilibrium. I hope this result is not a surprise to you, because you should have seen this result before, that tan alpha is equal to mu in limiting equilibrium in this scenario. But what we should do before we finish is to double check that it will not topple, and we can do that quite quickly by assuming it's on the point of toppling, so the centre of mass, although it doesn't look like it, is going to be vertically above this point here, and that is a distance and a distance. So the angle for toppling, tan of alpha, must be greater than a over a, which is 1. And we can see that tan of alpha is not greater than 1, so it will not topple. Therefore, if mu is less than 1/2, it will definitely slide down the slope. The cube is now replaced by a uniform solid cylinder of mass m, base radius a, and height 6a. Show that if mu is greater than 1/2, the cylinder will topple about the lower edge. So we've got the same plane. This is still alpha. Tan alpha is still equal to 1/2, but instead of a cube we have a cylinder, and I'm going to make it fairly tall so that the centre of mass is above the point of the edge of the base, so that it looks like it's about to topple. So the height is 6a, the radius here is a, the weight mg. We already know that if mu is greater than 1/2, it will not slide down the plane. So I don't need to worry about that. What we want to do then is to take moments about this point here. We have two other forces acting. Let me remember to put these on. We've got friction acting this way, and we know from the previous example that tan of alpha is equal to mu to be on the point of sliding, and in this case mu is greater than 1/2, so tan of alpha is less than mu, therefore it will not slide. So we know that straight away. Our other force is the reaction force, and I'm going to put that here in line with this point, because if we assume it's on the point of toppling, then this is the only point of contact left. So we've got R in this direction. Both of these have lines of action through the point. So if I take moments about this point, the only force I've got left is the weight. And you would say to me, but the weight is also going through this point. And it is. So how do we generate an equation when all of these have got perpendicular distance 0? The answer to that is we can split our weight into its component parts again. We've got mg sine of alpha down the plane and mg cosine of alpha into the plane. So taking moments about point A gives me mg sine alpha times by this distance, which is 3a, to give the clockwise moment, and that must equal the anti-clockwise moment, mg cosine alpha times by this distance, which is the radius a. Now if we simplify this by cancelling these and the a and then divide through by cos alpha and by 3 gives us tan alpha is equal to 1 over 3. So the information I've got so far is that it will not slide because tan of alpha is less than mu if tan of alpha equals a half, and we know mu is greater than a half. But now we've got tan alpha is equal to 1/3, and what that is specifically for is on the point of toppling. But I hope it's obvious that that's not what we've got. What we've got is tan alpha is equal to 1/2. Tan alpha is equal to 1/3 is when it would be just about to topple. So when we compare these two and say, okay, it would topple when tan alpha is equal to 1/3, what we've got is something even bigger than that. Tan alpha is equal to a half, therefore it must topple, because this is greater than what is needed to be on the point of toppling. So to answer this question, I would say tan alpha is equal to 1/2, which is greater than 1/3, therefore it will topple. And of course that also allows for this bit up here. We know it won't slide, therefore if the angle is bigger than this, it will topple. The next example is an exam question that we started in the previous video. We did part A, where we showed by integration that the y-coordinate of the centre of mass of the lamina is pi by 8, and we can see by symmetry that the x-coordinate is pi by 2. Part B says this: a uniform prism S has cross-section R. The prism is placed with its rectangular face on a table, inclined at an angle theta. The cross-section lies in the vertical plane, as shown. The table is sufficiently rough to prevent S sliding, so it will not slide. Given that S does not topple either, find the largest possible value of theta. So we're told outright that S does not slide. If we want the largest value of theta, we need to find the angle where it is on the point of toppling. Knowing the centre of mass makes this fairly straightforward. From here to here, this is a distance of pi by 2. And from the base of R up to here, this distance here is what was found in part A, pi by 8. For this to be on the point of toppling, although it doesn't look like it in the diagram, this point here must be directly above this point here, and this angle here becomes theta, the angle we're looking for. So having done the hard work in part A to find where this centre of mass is, now that we want to find the point of toppling, all we need to do is find the angle in this right angle triangle here. So the tan of theta is equal to pi by 2 over pi by 8, which simplifies to 4. Theta then is equal to the inverse tan of 4, which is 75.96 ... And if this is the angle where it is on the point of toppling, and we don't want it to topple, we just want to find the largest possible value, then this is the largest possible value. Anything bigger than this, and the prism will topple. So to one decimal place, our answer is 76.0. To finish this video and the chapter, a final exam question. A solid consists of a uniform solid hemisphere, radius r, and a uniform solid circular cylinder, also of radius r and height 3r. The circular face of the hemisphere is joined to one of the circular faces of the cylinder. So we have our cylinder, and on top of that, on this circular face, is a hemisphere. And they both have the same radius r, and the cylinder has a height of 3r. The other circular face of the cylinder has centre O. So that's down here, this is O. The mass per unit volume of the hemisphere is 3K, and the mass per unit volume of the cylinder is K. This is important, this is telling us their densities are not the same. So for the hemisphere, we've got a density of 3K, and for the cylinder, K. We're also going to need the volume. The volume for the hemisphere is equal to 2/3 pi r cubed, and the volume for the cylinder, pi r squared h, where h is equal to 3r, so that gives us 3 pi r cubed. show that the distance of the centre of mass of S, that's the full solid, from O is 9r over 4. So I'm going to use this as my origin so that I get this answer at the end. So we're going to have x here, y here, and put x bar equals 0 down in the corner straight away. So what we want to find then is y bar. Back to my table as per usual. We've got the cylinder, we've got the hemisphere, and then we've got the solid shape S. I'm going to have mass here rather than relative mass because we're going to include rho for the density. For the cylinder, that's k times 3 pi r cubed, and for the hemisphere, 3k times 2/3 pi r cubed. For the solid S, adding these two together, we get 5k pi r cubed. The y-coordinate of the centre of mass, y bar here. For the cylinder, it's at its geometric centre, so that's 3 over 2r. And from here, for the hemisphere, it's 3r plus 3/8 of r, which is 27 over 8r. Now I can form my equation, 9k pi r to the 4 over 2 plus 27k pi r to the 4 over 4 is equal to 5k pi r cubed y bar. K pi and r cubed cancel to give us 45 over 4r is equal to 5y bar, and therefore a final answer of y bar is equal to 9r over 4 as required in the question. Part B. The solid S is held in equilibrium by horizontal force of magnitude P. The circular face of S has one point in contact with a fixed rough horizontal plane and is inclined at an angle alpha to the horizontal. The force acts through the highest point of the circular face of S and in the vertical plane through the axis of the cylinder as shown. The coefficient of friction between S and the plane is mu. Given that S is on the point of slipping or sliding along the plane in the same direction as P, show that mu must equal this. So there are a few things that we know, which I'm going to put on the diagram. We know the centre of mass of this shape, here, say, is 9r over 4 up from O, and of course it's r from this side, due to the symmetry. We also know that here we've got friction acting this way, preventing it from sliding, and if it's on the point of slipping, then that friction is equal to, not less than, mu times r. We also have a reaction force which must be acting at this same point, because it's the only point in contact with the surface. And of course we have the mass of the solid S acting at this point here. And we had information about that from part A, but at this point I'm just going to call that mg for the weight. We can go back and find out what that was if we need to. Going through our usual things then, I'm going to resolve upwards. We've got r minus mg must equal 0, so r is equal to mg. Resolving to the right, we've got friction minus p must equal 0, therefore friction is equal to p. And because it's on the point of slipping, we know that that friction, and therefore also p, is equal to mu times r, and we know r is mg. So we've resolved, we've got the centre of mass, let's take moments. And this is going to be a really convenient point, because that will take r and friction out, and we'll get a connection between mg and p. So I'll call that point A, so I can refer to it here, moments about A. Anti-clockwise is equal to clockwise. Anti-clockwise, we've just got P, and that is acting at a perpendicular distance here. So this distance is 2r, the diameter of the base. So to get this distance here, same as this distance, if you want to look at this little triangle here, is 2r sine of alpha. So we've got P times 2r sine alpha. Clockwise moments is just the weight, and we need the perpendicular distance from here to here. This is a little bit more interesting because we need to find this in terms of alpha. And I'll be honest, when I first went through this question, it took me a little while to realize what to do here. But what we need to do is split this into manageable distances. This is the distance here that we want. A distance that's easy for us to get is this distance here. So if we can figure out this little distance in here and subtract it from this bigger distance, we can get the distance that we want. The reason this big distance is easy to get is because we know the center of mass position is 9r over 4, and this angle here is alpha. So this distance here, from O to this point here, is 9r over 4 sine of alpha. The little distance in green here then is what we want to subtract in order to get the distance we really want. And this distance here we know is the radius r. So this small distance in green is r cosine alpha. So to get the perpendicular distance of the weight from point A, which is this one, we need to take this and subtract this. And of course we're multiplying that by the force, which is the weight. Now we have an equation involving P, and we can rearrange that to substitute for P here, which we also know is equal to mu times mg. So if I expand these brackets, I get 2pr sine alpha is equal to 9r mg over 4 sine alpha minus mg r cos alpha. The r in each term can cancel, and if I divide through by sine alpha, that gets rid of that there, and we get sine alpha here, which is looking good because we've got cot alpha down here, and cos over sine is equal to cot. I'm also going to divide through by the 2 to get p by itself, so this will become an 8, and this will become over 2. That gives us p is equal to 9 mg over 8 minus mg cot alpha over 2, which I can equate to mu mg from this equation here. Then the m and the g cancel from each term, and we get mu is equal to 9 over 8 minus a half cot alpha, and if we force out a 1 over 8 factorizing, we get 9 minus 4 cot alpha as required in the question. I found the hardest part of that was figuring out how to get this distance here. Everything else was using the standard approach that we've done before. We used the center of mass location, resolving, taking moments, and the friction equation. I hope that's enough now for you to have a go at the questions in exercise 6b. You can also do the chapter 6 review exercise, and if this is the final video in M3 that you're watching, you can do the review exercise 2 and also the past paper. And I wish you all the very best with your exam.